Alright, let's have a look at a function and its derivative. So if we have a look at f of x, up until -2, the graph is said to be increasing. This aligns with the derivative where the graph is positive. As well, after 1, the graph is increasing, and this is also positive on the derivative. So those two sections line up. This middle section here that goes from -2 to 1 is decreasing, and on the derivative this is shown by the graph being negative. So if we were to have a look at the sign diagram of the derivative, we can see that when the derivative equals 0, we find out that x equals -2 and 1. And if I was to substitute numbers into the equation, if I had one, I would find out that we have positive, negative, and positive slopes. So having this information, I can then start to gather an idea about what my original function looks like. As well as knowing the slopes, I know that at -2 there would be a maximum, because the slope has been increasing and then decreasing. And at 1 there would be a minimum, because I am decreasing and then increasing. And so that corresponds to these shapes here and here. I could substitute in -2 and 1 into the original equation, and that would help me find out exactly where these points are here and here. Okay, now let's look at the second derivative. So I have all three graphs here, the original first and second derivative, and we're firstly going to look at the first and second derivative. So let's imagine you've found f dash x, and now you're finding f double dash x. They have a relationship in the same way as previous. So if we have a look at now, pink was my increasing. So where the graph is increasing is shown by positive graph on the derivative. And where the graph is decreasing aligns with the negative section of the derivative. And so I could draw a sign diagram for the derivative. And so when f double dash x equals 0, I find that x equals, so I'm looking at this point here, and it's about -1/2. And it's negative on the left and positive on the right. So although these two have a relationship, we don't often use that, because what we really want to do is use ways where our second derivative can help us to graph our first derivative. So one thing we've learned is that there is a spot on our first graph at -1/2, so around there, which lines up on the graph around here. This spot is called a point of inflection. Now, we've talked about maximums and minimums, and they are stationary points. And another type of stationary point is when we have a point of inflection. So the graph is stationary because it comes to a 0 slope, but it keeps going the same way. And we can go this way as well. So they are all our stationary points, where the graph at some point has a slope of 0. That's the stationary point. Our second derivative, however, helps us find this point where the graph does change in direction. Okay, it goes from being like a hill to a valley, and it changes at this pink dot. But it isn't a stationary point because the slope doesn't actually reach 0. It just changes. So what we can see is that our graph, and I'm going to use some new colors. Let's choose orange. Up until that point, although it appears to be, it increases and then decreases, if we have a look at the numbers of the slope, if I made up some slope numbers, let's imagine down here we have a very steep slope of 6. So it's a very steep line, sort of like this. Then the slope might become smaller, such as 5, so it's like this, 4, 3, 2, 1, until it gets to the 0 slope. So far the numbers have all becoming smaller. And if I look over the hill, I go -1 slope, -2, -3, and I'm making up these numbers just to show you though that for this whole orange section, the slope itself has become smaller from left to right. As the x has increased, the slope has become smaller for that whole section. And we call this section concave. It creates that cave or hill looking shape. After the point of inflection, the graph begins, or the slope begins, to get larger again. So let's choose yellow highlighter. So now for this whole section, let's choose yellow. Okay, so imagine maybe it goes back to -4, and then but -3, -2, -1, and 0 again. So now the numbers are actually getting larger. 1, 2, 3, 4, 5, 6, 7, and the slope's becoming very steep up here. And so this section is called convex, or concave upwards, as they call it in the textbook. And our second derivative helps us see that, because on the left-hand side of -½ whenever the second derivative, f double dash x, equals a negative, okay, so substituting in a number for x and you get a negative answer, that means that that section of the graph is always going to be concave. And so I might write that in pink. So when f double dash x is less than 0, we always end up with a concave shape. And when it is greater, we end up with a convex. Okay, concave, convex. When f double dash x is greater than 0, it is convex. Alrighty, next we're going to look at the same idea but without graphs. So starting with an equation f of x, we are going to find and classify all stationary points and non-stationary points of inflection. So as a general rule, our stationary points are going to be found with our first derivative and non-stationary with our second derivative. So the first thing we need to do is find our first derivative, which is 12x cubed take 48x squared plus 48x. And to find the points themselves, we need to make the derivative equal 0. To save time, I have paused and done that. So if you want to pause it and look at that, you can. Otherwise, we end up with the answers x equals 0 or 2. So our sign diagram for the first derivative has a 0 and a 2. And if I substitute in numbers less than 0, I will get negative answers. Between them positive, and over 2 is also positive. So we want to use this to think about how our f of x would look like. We're not really concerned with what the derivative looks like. And so what we do know is that, let's go purple, we have the 0 is at a minimum because the slope goes from negative to positive. And at 2, we have a stationary point of inflection because it's positive and then positive, but it has a flat 0 slope at the point 2. And so I'm thinking the graph looks something like this altogether. Stationary point and the minimum. So let's now look at what these points actually are. So we know that at the point x equals 0, we have is a minimum. And we can find out that point by substituting into the original equation, and it equals 9. So that point is 0, 9. Oops, sorry, negative 9. We can also find out that at x equals 2, which is our stationary point of inflection, so f of 2 equals 7, so that point is at 2, 7. Okay, so we're starting to gather what our graph looks like. The next thing we're going to look at is finding the non-stationary points of inflection. So this requires our second derivative, which equals 36x squared, take 96x plus 48, and again I'm going to pull. Okay, and we get answers of 2 and 2/3. Now we can draw the sign diagram for our second derivative, and I am just going to try and line up. So there is a 2, so I'm going to put that 2 there, and the 2/3 would be around here. So there's no 0 on our second derivative that we found, but I'm just going to remember that that 0 goes there. So if I substitute in my numbers into my second derivative, I find out that it is positive, negative, positive. Now on the first derivative, these help us find if there is a minimum, maximum, or stationary point of inflection. However, on our second derivative, it's a little bit different. It tells us about the shape of those slopes. So one thing is, so we have when it is positive, it is convex. Negative is concave, this way, convex, and then convex again, positive. Okay, so one thing is that we have a 2 on both of our derivative answers, and this means that because our second derivative finds out our inflection points. Now some of those might be stationary ones that we've already found. So we actually already found that 2, and if you think about something going concave and then turning to be convex, so that being the concave part, and then convex, that is the same shape as up here that we already knew about. That's a stationary point of inflection. So they're matching up. The one that we hadn't found is that at 2/3 we change from being convex to concave. So we know that at 0 there is the turning point of a minimum. So I guess that point 2/3 is where the graph starts to turn into this graph here. So if that's like that, that's at where the 2/3 is, and this is at where the 0 is. So the 0 is the turning point. The 2/3 is that stationary point where we change from being the convex part of the minimum into the concave part of the next section of the graph. So what we actually need to write though is that we have when x equals 2 is our stationary, which is given above. So again, we're substituting those into the original, so you're going to get 2, 7 again. That's not going to change. But we have found out that at 2/3 we have a non-stationary point of inflection. And we can substitute that into the original, and we get 2/3 and negative 2.48 rounded. Okay, so a couple of other things you might get asked to do. Okay, a common question is find the intervals where the function is increasing or decreasing. So this uses our first derivative, and we can see that the graph is, so f of x is increasing. Go back up here, we can see that it's increasing for both of these sections, so really anything above 0. However, it would be good to show that at 2 there is a slope of 0. So we could write that as increasing for 0, x is greater than 0 and less than 2, or for when x is greater than 2 but not equal to 2. And f of x is decreasing, and that was our first section for when x is less than 0. Another common question you might come across is where is it concave or convex? And I won't write it out properly. And that is where we use our second derivative, and we sort of already talked about that. So we can see that it's less than 2/3 or greater than 2 for convex. X is less than 2/3 or when X is greater than 2. Get that right? Yes. The reason we don't use and there is because we're not saying X has to be both those things at the same time. We're saying X when X is less than 2/3 or when it's greater than 2, the graph is convex. And for concave, that was when X was between those two things. Now you'll notice the textbook uses the equal sign for all of these things, and Mrs. Hancock and I both don't go with the or equal to, because in between all of those points there is a point where it is 0 or stopping or changing. So we're leaving our answers as this. The last thing that you'll be asked to do, and this is the important one, sketch the original graph. So we're pretending that we don't have our calculators with us because we won't have it in the test, and we're going to use our derivatives and everything we found to sketch the graph. So you can go back and have a look at stuff if you want to. However, at 2, and we're making these quite small, 7, we have the point 2,7, and that was our stationary inflection. So one of these, oops, not so much, maybe more like this. And at the point 0, -9, so maybe here, we had our minimum. And we also had our non-stationary point of inflection at 2/3, maybe here, -2.4, so maybe in here. That was 2/3, -2.48. Now a non-stationary is when the graph might be like this and it's here. So it's not at a flat point on the graph horizontally. So this one has horizontally a 0. This one does not have that. And so a quick sketch of our graph is going to look like this. Oops, no, I haven't really done it very nicely. I can't do it. I hope you know what I'm trying to do. So try to turn it, go through there. I need the flat point. Oh, that's a bit better. So there has to be a flat point at the stationary, but you can't really tell about the non-stationary. You can't really see that very well. There's nothing really that happens there. Now, the other reason, how did I know to start up here and end up here? Well, it is a cubic. If I had any other, there's no other turning point. I can't have anything going back the other way. So I've just got to start up here and head towards my first, and I know that has to be that minimum shape, and then I know it has to have this shape at this point here. And so really I'm just drawing to suit those things. Alrighty, long video. See you later.